everyone. My name is Dr. Charlene Ortiz, and today we are going to be covering statistics or a review of statistics, particularly related to the quantitative methods of this section. Today, we are going to be talking about hypotheses, experiments, and normal distribution. By the same token, we're also going to be covering randomization and random assignment of participants. We're also going to be talking about descriptive and inferential statistics. We're also going to talk about correlations and central tendencies of data. In addition, we're also going to be talking about error bars and parametric and non-parametric statistics. And lastly, we are also going to be talking about the significance and effect size. So let's get started. One of the first things that I would like to talk about today is the null hypothesis testing. And what do I mean by null hypothesis? Whenever we are trying to test data, whenever we are trying to look into a review or a prediction of data. So for example, if I were to say when A happens, B will occur, we're thinking about a prediction, right? We're thinking about a hypothesis. So in a very basic sense, I should say, a hypothesis is simply a prediction that we're trying to understand whether or not we're going to accept or reject. What do I mean by accept or reject? Well, one of the first things that I would like to show you is that we will have a null hypothesis. And with a null hypothesis, what I mean is that there will be no effect on the treatment that we are trying to infer or give to a participant, meaning that there was no change, there was no effect. By the same token, we generally refer to this as a control. A control is simply a measure or a group of people that simply were not exposed or are not impacted by that treatment. So let's think about the usage, I should say, of a new medication. Some participants are going to receive this medication, and some participants will not receive the medication. And the point would be to understand whether or not that treatment, if it had an impact towards that group. So notice that with the null hypothesis, what I'm trying to say, there will be no change. There will be no effect with that treatment. However, what we're interested in is finding out, is there indeed an impact? Is there indeed a factor that we can measure because of this treatment that we are giving to this group of participants? So that's what we normally refer as research or alternate hypothesis. In this regard, we're trying to ascertain if the treatment did indeed have an effect, or is it different from the control that we initially found. Now, something important that we need to cover is an experiment. One of the first things that I need to make sure that's relayed to the audience is that experiment, the point of an experiment is to ascertain and establish whether or not there was a cause or effect in the relationship between an independent variable and the dependent variable. And how do we do this? Well, with the independent variable, I should say, we always want to ensure that we have some form of manipulation. Now, with the dependent variable, what we're trying to do is to measure. So in keeping with our example of that medication, this fictitious medication, the manipulation would be, say, for example, how are we going to produce and give this medication to that group? So for example, how many milligrams, what time of day, right? So in this case, the medication is the independent variable. and the amount of milligrams that we are giving to the participants. It's how we are manipulating that independent variable. So notice that the value of that independent variable relies on its manipulation. Now let's think about the dependent variable. The dependent variable, what it means is that I'm trying to measure that difference, whether or not there was a difference that I can indeed measure. So let's think about that medication. Say I have a group of people that are willing participants and voluntarily accepted to take this medication for the study. Now, say, for example, this medication is brand new for, let's talk about anxiety. What I would try to see is whether or not this medication did indeed have an impact, say, for instance, in the reduction of symptoms with that specific group that was experiencing symptoms of anxiety or perhaps a diagnosis of anxiety. So in this case, the amount of milligrams and that medication will be the independent variable that's being manipulated, and keep that in mind. And on the other hand, I'm trying to measure the impact from this medication towards that dependent variable, the one that depends upon that independent variable. Now, something to note is that in an experiment, we are also immensely focused on how we can control this situation. Why is that? We are trying to control the situation of this experiment because I am trying to reduce the influence of other variables that are outside of my experiment. So let's think about that for a second. Why is it so important that in an experiment, I try to control and try to minimize the impacts of other things, of other variables that could be affecting that measure? Let's think about this. Say, for example, in the same group, and keeping with that same group that we're thinking about, the willing participants that are taking this medication for anxiety. Let's think about what other factors can contribute to perhaps not getting good information. If I can control for other factors, for example, I can control, say you're only going to take this medication at 6 p.m. every day after dinner. Notice that I am trying to control other factors that could influence the effectiveness or the manipulation of this independent variable, which in this case is the medication. So for some medications, it is needed that the person eats before or after taking the medication. So that is a variable that is outside of their experiment, but that I am trying to control because I want to make sure that the only thing that is impacting that dependent variable, so my anxiety, is solely that medication, that independent variable. I want to guarantee that that medication, or perhaps reduce the chances that there are other factors outside of my experiment that are going to be affecting that measurement of my dependent variable. So in this case, we're thinking about anxiety and this medication. Now, remember, as I stated earlier, the independent variable relies on its manipulation. And in regards to the dependent variable, we are looking into the measurement. Now let's look at what this basic manipulation would look like in perhaps a study. So notice that a good way to remember which one of the factors are we talking about is that manipulation. We can think about independent variable. So IPIN, which is a really good acronym in order to remember which one is the one that is the manipulation that's imparting that manipulation, and then which one is being manipulated or measured. Something really important to mention is that independent variables will have something that we call groups, conditions, or levels. And what do I mean by that? Well, let's look at this independent variable here, which is gender, although this would apply better to a, not necessarily a true experiment, but perhaps a quasi-experiment approach, which if you watch the previous lessons, you'll know that this is the case where we can't indeed manipulate the independent variable, but we can select individuals who have that independent variables, for example, gender, right? I can't assign gender to a person, but I can indeed recruit participants that identify as man, woman, and non-binary, and so on and so forth. So notice that this independent variable here had at least 3 levels, right? So we have 1, 2, and 3. I don't want you to think that one is greater than the other. I don't want you to think that one level is better. So for example, saying men is assigned a 1, woman is assigned a 2, and non-binary is assigned a 3. This doesn't imply necessarily a sort of hierarchy. This is simply different methods, right? Different, or I should say groups or levels of that independent variable. So I don't want you to think that these levels, because they are different levels, it doesn't necessarily imply that there's a hierarchy that one's better than the other. What I am saying is that because of these levels, there's always going to be different groups. So let's go back to our example. We're giving this medication to a group of participants, and these participants are going to be divided in, say, man, woman, and non-binary. And we're trying to identify whether or not if this medication has a certain impact, and it might be different, for example, for men, women, and non-binary. So notice that it doesn't imply that one's better than the other. It's simply that there are different levels to that variable. Now, let's go back to our dependent variable. And as I stated, the dependent variable is that is going to be measured. So this is another way to remember which one is the measurement variable. So let's look at ways that we can actually conduct that measurement, right? Because in the sense of a dependent variable, the whole point is for us to identify that measurement, to see whether or not there was indeed a difference between persons who received the treatment, i.e. medication, or participants that did not receive it. Let's look at units of measurement. How can we gather that data? Well, perhaps we can use rating, right? We can use a form of rating. Say we can do one prior and after the medication has been taken for a pre-established amount of time. We could also conduct scores. We can do scoring based on Beck anxiety inventory in keeping with our example. So notice that we can have some sort of score from an assessment or a rating, perhaps given by the actual participant. And maybe we can count the amount of panic attacks as described by the participant by a pre-established definition during our experiments. There are many ways that we can actually gather this information for us to determine that measurement, which is the whole intent of, it's the entire intent, I should say, of an experiment, to determine whether or not there was indeed a difference, right? There was indeed a difference between those who were not impacted by the treatment and those who were impacted or did receive, I should say, the treatment. Now, as a review, we did talk about data scales in previous videos, and I highly recommend, if you haven't watched them, to please go ahead and review these videos, because there is a very in-depth discussion of each of these scales. But as a review, as a very short, brief review, we're talking about nominal scales, ordinal scales, interval scales, and lastly, our ratio scales. And when we're thinking about our nominal scales, we are generally referring to categories, right? So for example, we're simply trying to put a set of information in a bin. So for example, we can assign men a number 1, women a number 2, and so on and so forth. This does not imply, again, that there is some sort of better status, I should say, because of the number. It's simply we are putting things in a category. Quite literally, we're trying to put that information in a box. So the men belong to this box for the assessment and the review of this medication, for example, and women belong to this second box. And say, for example, non-binary people can belong to this third box. It doesn't imply that one's better than the other. It's simply we're trying to sort out the information in different categories or boxes, if you will. Now, in keeping with our review, let's talk about ordinal scales or ordinal scales. In this regard, what we are thinking about is some sort of hierarchy, some sort of rank. Now, a good example of that would be the birth order, whether you're the first, second, or third child in your family. Another scale to consider in this case will be the interval scale. Now, with the interval scale, these differences that perhaps were not necessarily meaningful in our previous scales, right? These differences that were perhaps not meaningful with our nominal, and ordinal, I should say. Here we are seeing more meaningful differences. So now being number 1 or number 2, there is indeed a reason that these numbers are different, right? There is data that we can, or information that we can ascertain and we can analyze from because there is a difference in number. Now, something to remember is that there is in fact no true zero. What do I mean by no true zero? Well, if you recall from previous lectures, what we mean is that in this regard, the number 0 doesn't in fact mean 0. It doesn't in fact mean nothing, right? So one of the examples that we talked about and that we can talk about today is IQ, right? So when we say an IQ of 0, we don't necessarily mean that the person has no intelligence, right? That 0 literally means 0. In this case, there's no true 0. But if we move to our another scale, I should say, that I'll share with you, notice that there is, in fact, a ratio scale. And in this case, there is indeed a true 0. So in this regard, 0 actually means 0. If you are 0 years old, means you are non-existent, right? You haven't been born, right? So when we do have a 0, it actually indeed means 0. That there is nothing there, right? There's a true 0. Now let's talk about normal distribution. And this may come across as a little bit complicated at first, but it's actually an immensely easy way for us to understand how data, how results are distributed and how they are found in the population. So one of the things to mention is that normal distribution is symmetrical, right? And what do I mean? When we have all this information, so in keeping with our example, our previous example of IQ, right? Keeping with our example of IQ, notice that if we're thinking about IQ as a normal distribution, means that all of this data that you see here, every single piece of information, so Billy falling in here, and then Rebecca getting her IQ test and following around here, and then Jessica, she fell under here, but Juan did really well in the IQ test, so he falls within here. notice that in this information, they have been distributed along this line. They have been distributed. And that means that if I were to cut this line down the middle here, notice that this side looks exactly the same as this side over here. There's the same shape, right? So this side, this red line here, looks exactly like this red line here. And this yellow line looks exactly the same here and looks exactly the same on the other side. So notice that that is one of the main characteristics of a normal distribution, is that it actually looks the same from both sides if you were to split it down this middle here. Another characteristic is that it looks like it has a bell-shaped curve, right? So it looks like a bell. Why does it have that bell? Well, it's because of characteristics from the mean, the median, and the mode, right? So let's talk about the mean first, okay? The mean is basically the average, right? The mean would be the sum of all the values that you came across during that study. And we're going to add up all of those results. And we're going to divide it between the amount of values. So for example, we have Juan here, and he had a specific number for IQ, and D here, we're going to find the mean of IQ, which is generally 100. So we have Juan over here, we have Peter over here, we have Robert out here. So notice that based on this information, this number, we would add the numbers of all participants. So whatever his score was, whatever Robert's score was, whatever Juan's score was, and we're going to add all those numbers and divide it by 3 because we have 3 participants in this study. Now let's talk about the mean, right? Or let's say the median. The median is simply that number, that middle number that we will find when we rank all results in order, right? From lowest to highest. So let's think about 1, 2, 3, 4, 5. So notice that all of these results are in order. And the median will simply be that number that we find in the middle after they've been sorted. But what if I have these numbers like this? So we have 2, we have 3, we have 1, and we have 5. So which one would be the median? Well, it will still remain the same, because as we know, when we sorted them, when they were in order, notice that this was the number 3 was the number that we had in the middle. Now, the next thing that we would like to cover in the normal distribution is the mode. And the mode is simply that number that we found that was more frequently found in that data, right? So for example, if I have these numbers here, some random numbers, think about which number here is found the most. Well, in this case, we have 2 6s, right? Right here. So 6 would be my mode, right? Because it's a number that we have found most frequently that keeps repeating itself. Interestingly, we can use a normal distribution to illustrate many different features. We can illustrate it, say, perhaps to illustrate IQ. We can use it to illustrate the average or the most normal distribution, say, for instance, about weight. So we can actually use this shape to illustrate a vast majority, many types of data. Now, in addition, this figure here is going to represent multiple normal distributions, right? So for example, if we look at this red one, right? Notice that the red one has a really high peak, right? In comparison, say, with the purple one, right? Where the purple one is actually pretty low. So the mean here and the purple, notice how their variance, and variance, what we mean by variance is how far we move from the average here. So the mean. So we're talking about variance. How much am I moving away from that center? How far away am I moving from that mean? So notice that here for the red one, we find that variance here. Whereas for the purple one, we are finding it here. The red one suggests that the vast majority of the data that's in the middle, the vast majority of respondents for some reason were average Joes. So the vast majority of the information that we gathered, say for example, on this IQ examination, the vast majority of individuals fell within the middle, fell really close to that average. Whereas in the purple example, the vast majority of the individuals fell within the extremes, right? So 1, 2, 3, 4 standard deviations, both to the left and the right. So notice that the results were a little bit more extreme. Either they scored really low or they scored very well on the assessment. That will be the case of the purple. So that's what this shape is telling me. Whereas on the red one, what it's telling me is that the average, a lot of people in this examination scored within the average. Now, this is important because when we are talking about a normal distribution, and I'm going to move this to the side as to not be in the way. Something immensely important about a normal distribution is that we can ascertain how much information or how many participants fall within a specific distance of this standard deviation. And standard deviation, we generally represent it with this symbol here, which is the sigma. So sigma is representative of that standard deviation. And like I said, standard deviation is how far are we moving from this center, from the mean, right? Did I move 1 time, 2 times, 3 times towards the negative, or 1 time, 2 times, 3 times towards the positive? With this information, we can find out, if we look at this table, at this illustration, I should say, we can find out that within 1 standard deviation, so within this line here, in this line here, notice that about 68% of the population will fall within this section, within 1 standard deviation. Now let's look at 2 standard deviations. So if I were to look at all the information here and all the information here, right? We're going to add it to that red, and I'm using colors just simply for illustration purposes. Notice that everybody within these 2 lines, so from here to here, everybody within here generally falls within 95%. So 2 standard deviation means that about 95% of those individuals during that assessment will fall within 2 standard deviations. Now, lastly, let's think about the next group. Well, usually I want you to notice how far we're moving from this mean, right? We're moving pretty far. This was 1 standard. This is 2 standard deviation. And again, 1 standard, 2 standard deviations. So we're moving pretty far towards this direction. The further away we're moving from this standard deviation, the further away we are from that mean, and the less amount of population. How do we know that? Because in here, within this group here, technically this line, these 2 lines here never touch, right? They move towards infinity without ever touching. So notice that within here, we're going to find about 99.7% of all that data. It's going to be included within 3 standard deviations. So in this case, 1, 2, 3 standard deviations, and 1, 2, 3 standard deviations. So this would be the information normally distributed. And I'll give you an example. So let's think about IQ again, as in continuing with this sample. So the average IQ will fall here, right? Because this is our average number. And generally, the average IQ is of 100, right? The average person. And to my understanding, if I'm not mistaken, the standard deviation for intelligence, I believe, is 15. So 1 standard deviation, if we add 15, it will be 115. Standard deviation minus 100 will be 85. So notice if Peter scored a 85 and Robert scored 115, they still fall within 1 standard deviation. They would still be considered part of the normal range, the average range of intelligence, because they fall within this section right here. Now, once we start moving a little bit further, if we have, say, for example, Joanna, right? We have Joanna. Now we're talking about we're moving in the range of 60. We're moving pretty further away. And then over here, we start moving. Let's think about Maria. Maria gets a score of 130. And then Joanna starts falling more in the range of 70. Notice that now we are moving 2 standard deviations, so 1 and 2, 1 and 2 from this mean here. That's a pretty straight line if I've ever seen one, huh? Which tells me that now we would say that this score here is above average, because remember, the scores that were within here were still average, but now we're seeing scores a little bit further away from this average in the middle. So as you can see, we're starting to move further away. And then if we start getting scores, say, for example, Kendrick, and Kendrick scores a 145 in his IQ examination. And then we have Noah, and Noah starts scoring in the sense of 50, for example. And notice they are falling within that 99.7, right? They're falling in that very rare, very few amount of data, right? So this is what we will call very below average or very above average, right? Because we're falling 3 standard deviations from this average or mean here. Now let's talk about randomization. Randomization gives us the best reflection of the population. What does that mean? It's telling me that everybody in this population will have an equal chance of being selected, right? So let's think about the assessment that we were looking into for IQ. If I were to conduct this IQ assessment, this IQ experiment on, say, your future university, right? And, Happy College Incorporated, right? So say we're going to conduct this study in Happy College, and I want to conduct this study. I would have to make sure that this study and the participants I select had an equal chance of being selected. Why is that? Well, because I don't want my results to be skewed, whether it be in one direction positive or one direction negative. I always want to make sure that it represents that normal curve that you saw earlier. Why is that? Well, because I don't want my results to be biased. Say, for example, I go to Happy College and start recruiting people for this experiment on IQ or this assessment on IQ, but I only select students from their honors section or honor students or students that made it to the dean's list. So notice that in this case, if we go back to our slides, those results are not, these participants didn't have an equal chance of being selected, because now if I have these participants that are always in the honors class, generally they are performing above average, right? So one could infer that their scores are also going to be above average, right? Or perhaps very above average. So that's one of the reasons why we wouldn't want to gather data from participants that did not have an equal chance of being selected. Another thing is that randomization involves two steps. It involves two processes. The first process is random selection. What is random selection? I want to select this group of people in a way that it can actually reflect that larger population. So I'll give you an example. Say we go to Happy College, right? And this is what that college population looks like. But then, we have different people, right? So we have different types of people in that college, right? Regarding their practices or their majors or year of college, right? Freshman, sophomore. But then when I try to gather a sample from this big population of Happy College, right? Notice that I'm only going to pick students that were in the honors course. Now tell me, do you think this is actually a representative sample of Happy College? Well, of course not, because we have other types of individuals. So we want to make sure that I randomly selected all of these individuals into my sample, right? That they actually reflect that population that I am trying to investigate, right? That I'm trying to conduct a study for. I want that sample to be representative of this larger population. Not only that, my second step would be random assignments. So now that I have my little sample, right? I have my little sample of all of Happy College, right? And I consider that this is a representative sample, and there are statistical ways to infer this. I want to make sure that when I give them and they are part of my study, I also want to assign them to the groups. So for example, the group that had no medication, right? In keeping with our first example, so no medication, the group that received medication, and perhaps a group who received a placebo, right? I want to make sure that all of these participants had a random assignment to each of these groups, right? I don't want to say, well, I only want the people who have less anxiety to be on my medication group. Why is that? Well, because it's going to look like the medication had a great effect, right? So I want to make sure that everybody had a random chance to be assigned to all the levels or all the groups of that independent variable. Interestingly, when we are talking about random assignment, we need to think about that subject does not have a choice on that experimental group. Which group are they going to be assigned to? Interestingly, something else that we need to mention is that we need to have everything exactly the same for that control group, for example, the group that's not receiving that medication. And we want to make it look and have the same, not treatment necessarily, because that's why they are the control group, but the same environment, the same random assignment, the same random selection. We want to make sure that all of the conditions are the same except for that treatment. Now, we also want it to be proportionate, right? So if in my happy college, it's about 50% women and 50% male, I don't want my study to be, let's say, those who are receiving the treatment are 70% male. Well, that's not necessarily proportionate to that greater, right? That greater population. So the students in happy college, because it was about 50-50. So I want to make sure that that data, when we are assigning someone to those levels or to those groups, want to make sure that it is proportionate to that greater group. The reason we do this is because we want nothing else to have an impact other than our treatment, right? We want nothing else that's going to have some sort of influence towards my dependent variable. Say, for example, having a group that's 70% male, when we know for a fact that happy college it's about 50-50. So we want to make sure that that doesn't become a factor that's going to influence the study of this variable. Now, how is it that we understand these inferences? How is it that we understand how that variable is being manipulated, how that variable is being measured? Well, we use statistics. Statistics are simply analytical tools. And an analysis, it's simply a way that we can gather new information from a set of data, right? We can conclude and gather certain pieces of information based on previous information, right? In order for us to conduct statistics, we have to assume that most characteristics fall within the normal curve, right? So we have to assume that it generally looks like something like this, right? It looks like this specific curve, and it doesn't look a little bit skewed, or not skewed necessarily. That wouldn't be the correct term, but it doesn't look like there's a conglomerate of mean differences, right? We don't want it to look so sharp as this red one. We would like that distribution to be a little bit more even when it comes to our normal curve. Another important factor is that when we assign these people randomly to these treatment groups, so if you recall, we have the medication group, no medication group, and the placebo group, we want to make sure that the distribution is represented here in the sample, right? So we don't want them to be not representative of this greater normal sample. You always want to make sure that they are indeed representative. And we do so because we want to, in fact, measure the changes. We want to measure those changes from that dependent variable and from them to be attributed solely on that manipulation. There are different types of statistics that we can use, right? And the first type that we can use are descriptive statistics. The important thing about descriptive statistics is that they tend to summarize a pool of data. And you actually just observed this a little bit earlier because we spoke about the mean and we spoke about the standard deviation. Now, these types of information, we can also consider them first and foremost, the measures of central tendency, I should say. So let's think about the mean, right? What's central, I should say, tendency in that curve? Now, we also have measures of variability, which is what you saw earlier, right? So we have our mean and how much in that standard deviation are we going to vary, and we're going to navigate further from that mean. So how further along are we going? The standard deviation and standard error of variance, right? How much are we moving away further from that mean? That's also a form of descriptive statistics. So another thing we can look into when it comes to descriptive statistics is our, excuse me, our correlation coefficient. So we're trying to determine that linearity with an R, or what is our correlation coefficient. So every time you see R, I want you to think about a correlation. Now, we've talked about correlations before, but very, very shortly as a review, a correlation, it's simply a relationship between one variable and the next. So for instance, when A occurs, when A increases, B increases. When A increases, B decreases. Or if A decreases, B will decrease. So that is a correlation, right? It doesn't necessarily imply a cause. It doesn't mean that A is causing B. What it means is that simply when this happens, this will happen, or this can happen. So if A goes up, B goes up. If A goes up, B goes down. Or if A goes down, B goes down, right? So that is simply a relationship between these two. Now, moving along with other forms of statistics, we just spoke about descriptive, but now we're going to talk about inferential statistics. And what do I mean by inferential statistics? Well, previously, what we were looking into, right? We were looking into the description of that pool of data because we're trying to summarize, right? So it's simply, whenever you hear descriptive statistics, I want you to think about just the summary of all of that data. But when we move along inferential statistics, now I want you to start thinking about the probability that any change occurred by chance. So that's what inferential statistics provide to us. Descriptive provides a summary of this data, whereas inferential statistics, now we're actually conducting an assessment. We're moving a little bit more in detail. So let's think about our example of this medication for anxiety, right? We have that group that received that medication. And I think I normally use this example. So say you're here, there's this medication, and we showed in our studies that the group that received the medication actually started experiencing less symptoms of anxiety. Well, that's fantastic. But can we actually say that it was because of that medication, right? Can we actually conclude that it was because of that medication? Because inferential statistics would tell us if it just happened by chance, right? Let's say that those participants did do better, but it might have been simply because that would have been the natural order of things, that they would have actually be better and recover or experience less symptoms of anxiety simply because that would have been the natural order of things because of chance. It's simply, they would have simply been doing better irrespective of that medication or the amount of milligrams. Now, the only way to do that is by conducting inferential statistics, whether or not a treatment was beneficial other than because of chance. Well, that's why inferential statistics are very important. Descriptive statistics will tell us what the data looks like. It's a summary of the data. And inferential statistics goes a little bit deeper and tells us a little bit more of, let's assess the probability of whether or not these differences occurred by chance. Now, there are two types of inferential statistics that we will be covering here today. The first one is a parametric statistic. Now, some of the things that we will need to consider is whether or not things that occur were statistically significant. Now, that's something that I should mention before we continue. And what do I mean by statistically significant? When I talk about something that's statistically significant, let's think about that example of the differences, like these individuals, when they took this medication, their symptoms actually reduced, their anxiety symptoms, which is fantastic. But we want to find out whether this difference is statistically significant. Because for all we know, when we measure that dependent variable, when we measure that variable of anxiety, it turns out that that significance was negligible. That difference didn't actually have a great impact. So yes, did it reduce the symptoms? Okay, sure. We can prove that it showed that or we can demonstrate, which would be a better term, we can demonstrate that that medication did actually reduce the symptoms, but was it significant enough? And the way to do that is through inferential statistics. So before I continue, that is something that I should bring to your attention. Now, with parametric statistics, we can use a t-test, which is usually represented by the letter T, or we can usually use an analysis of variance, usually represented by its acronym ANOVA or by its statistical symbol of F. Now, there are some assumptions. There are some assumptions that need to be met in order for us to be able to use parametric statistics, right? And these assumptions are, we generally assume that there is a normal distribution of that data. So basically, one of the first things that we have to assume is that the data would look like your normal curve, right? It will look like your normal bell shape, and that it is not skewed from one side to the other. So that's one of the first assumptions that we need to meet, is that this data is indeed normally distributed. The other thing, if you remember from our previous slides, in order for us to conduct parametric statistics, I should say, that data had to be investigated through an interval or ratio scale. That data must be in an interval or ratio scale. And if you remember from earlier and from our previous lectures, remember that in the interval and ratio scales, we start moving towards negative numbers. We start moving towards a true zero. The differences in these numbers are actually meaningful. So in order for us to conduct parametric statistics, I should say, one of these two data sets or scales have to be used in order for us to meet that assumption. Now, another assumption that I would like to address is that the sample size, it has to be sufficient. And generally, this falls within the realm of 20 plus subjects or participants. So if you remember from my sample of Happy College, right? So this is the entire population of Happy College. In Happy College, say we have about 2,000 students. And in order for me to conduct a parametric test, when I draw my sample, right, when I draw my little sample, I have to make sure that it is at least 20 participants. Now, later, we're going to cover a little bit more in detail, and in today's lecture and other lectures, we're going to cover why exactly is sample size important, right? Why is it that having a larger size may be beneficial? Why is it that having a small size can be detrimental? Although in some qualitative features, we want a smaller size, but in the quantitative sense, which is what we're talking about today, why is it that we care so much about sample size? We will be covering that, but do note that in order for us to conduct a parametric statistic, we would need to have a sample of at least that much. Now, if for whatever reason, when we are collecting our data, we find that we do not meet any or one of these assumptions, so if we violate any of these assumptions, we must then move to non-parametric statistics. So for example, your bell didn't look like it was normally distributed. You were unable to use interval or ratio data. So now you're moving towards the nominal and ordinal. Or your sample turned out to be less than 20. You must now not utilize parametric statistics, and we're going to move non-parametric statistics. Now, generally, when we are moving towards the non-parametric statistics, one of the methods that we can utilize is chi-square, represented by the chi symbol squared. And for those of you who will be taking statistics, you will actually be conducting these types of assessments and procedures yourself. For the purposes of this lecture, however, we will not be conducting a chi-square. Now, as I was stating earlier, let's talk about correlations, or that R value that I mentioned earlier. Relationships do not imply causation. If you don't take anything else from this lecture, remember that a relationship does not imply a cause, right? Just because something is related does not mean that one caused the other. Just because you are related to your siblings does not mean that you caused your sibling to be, right? So your parents were the ones that caused your sibling to be. So notice, just because there is a relationship between variables, it doesn't necessarily mean that one caused the other. And this is immensely important, particularly because, especially in the social sciences and psychology and things of that nature, we are bombarded with information from the media saying, oh, they found a relationship between A and B, and then the public decides to consume that information. The problem with that is that just because we had that relationship, it doesn't mean necessarily that there was a cause, right? There could be a relationship between one factor and the other, but remember that that does not necessarily imply a cause. Now, we would expect that things that are causing one and the other are related, but not everything that's related is causal, right? So that's something to keep in mind, especially when you become a consumer of research yourself, or if you observe that someone else is becoming a consumer of research and they start making decisions based on their misconception that there could be a cause. Why is it that we cannot use a correlation, right, or R value? Why is it that we cannot determine cause and effect? Well, it's simply because there is a third factor, right, that we don't know about. We don't know where it comes from. Now, let's look at it from another aspect, right? And I like using this example because it tends to stick with students really well. So there is indeed a relationship between shoe size and test performance, right? There's actually a positive relationship, positive R, positive relationship. So the larger the shoe size, right? So the change in the same direction, the better, the larger the test score. So notice that this is a positive relationship. The larger the shoe size, the better the test performance, the higher the score. And you're thinking, how is that possible? How is shoe size related in any way to test performance? It's because of this third factor, or unknown. Well, imagine a kindergartner, right? Their shoe size is pretty small, huh? Whereas a college student, right, their shoe size is pretty big. So if I give a kindergartner a calculus test, chances are he or she is going to perform poorly. Whereas my college student, they have been doing math their entire life. They probably already took calculus. So chances are that this college student is going to perform better. So notice that the unknown third factor here was education. This was the cause. This was the cause of having a better test score. The cause wasn't the shoe size. There is a relationship between shoe size and test score simply because you have actually been in school longer. You've received more education. Therefore, you have more preparation. Say, for example, if I give you that calculus exam. So notice that that's why we cannot use a relationship. So for example, shoe size with test score, because the cause was this third factor right here, which in this case was education. Now, just as for me to reemphasize, is a positive relationship is that both X and Y will change in the same direction. So if X goes up, Y will go up, will increase. By the same token, if X goes down, Y will go down. So this is considered a positive relationship, right? Positive R. I don't want you to think that positive means more or less and negative means more or less. Positive simply means same direction and negative means opposite direction, okay? So I don't want you to think that one's better than the other or the one increases, the other decreases. It's simply positive, same direction, negative, opposite direction. So in order for us to illustrate a negative relationship, if Y goes up, remember it's the opposite direction, right? Means that Y goes down. By the same token, if X goes down, that means that Y goes up, right? So in our example earlier about that fictitious medication, say the more of that anxiety medication that a person was taking, the less anxiety symptoms they were experiencing. Therefore, this would be considered a negative relationship. One went up, the other one went down, right? The opposite direction. Now, we're also going to talk about test linearity. Why is that? It's actually a really interesting way to actually observe our data. We actually have an illustration of this later on. Notice that our relationship, it's either will have a symbol of positive or negative. So something that will move from my little scale right? And this is a 0. So here we have -1, 0, and +1. So whenever we have our results for a correlation, say for example, the shoe size was related to test performance, and when I ran that statistic, it actually gave me a really high number. So let's say 0.86, which is really close to a perfect relationship. The closer we are to this number, so the closer we are to either -1 or +1, the stronger that relationship is. If we find a number 0, the closer we are to this 0, the less likely that there is a relationship between those two variables. And here is a good example, right? Now we're actually going to see it plotted. Okay, I want you to think about each one of these little dots as a result, right? So this is Peter's height and weight. This is Jessica's height and weight. This is Kendrick's height and weight. This is Noah's height and weight. So I want you to think that each one of these little dots represents a response. We have my y, my x and y. So this is a positive correlation. If you remember, if x goes up, then y will go up, right? Meaning that both of these are going to go in the same direction. So the larger the weight, right? We're moving, this is a 0, moving that direction. And for y, that's a 0, and we're moving towards that direction. So notice that the higher the weight, right, the higher the height. Now let's look at this example, right? This is a negative correlation, right? So a negative correlation, if you remember, we are talking about the opposite direction, right? So when one increases, the other decreases, right? We're going the opposite direction. So again, this is a 0. We're moving towards that direction. This is an x. This is a y. X and y axis, and this is a 0, right? Wherever they meet, this is going to be a 0. So notice that the more hours of sleep we got, the less tired we felt. So notice that this is a negative relationship because as one went down, the other one went up, right? The more hours of sleep, the less tired this person reported to be. Now let's look at my 0, right? There is no relationship, right? You remember from here, the closer we are to a 0, the less relationship we have. So here, notice how here we have a little pattern, right? All these dots fall in a little nice line, and all of these are following a nice little line. So that implies a relationship. But when we're looking at no correlation, that's 0, right? Notice that all of these points are not really following an order, right? So it looks like it had a peak somewhere, and then the data is just simply literally scattered all over the place, right? So it seems like it was just scattered all around. Whereas here, you know, it generally follows a straight line, and here it generally follows a straight line. So what this tells me is when one went up, the other one went up, meaning there's a positive relationship. When one went up, the other one went down, different directions, therefore a negative relationship. And here, there was just simply no relationship. Everything, we can see it visually, but there is no relationship between hours of sleep and shoe size. Now, we actually talked about this a little bit earlier, right? Because we were talking about measures of central tendency. We already spoke about the mean, where the mean is generally represented by the letter M. And we have the mean is simply the sum of all those observations divided by the amount, the number of data points, right, of our sample. Generally, population and sample are represented by N and lowercase n respectively. Now, median, as you recall from earlier, will be that middle number when we start ranking our data, and we'll find that midpoint, right? So 1, 2, 3, 4, 5. And in this regard, notice that when they are ranked in order, our middle piece of information was the number 3. And the mode is simply the number that we find the most. So in this case, let's do here. So in this case, we find that the number that repeated itself more frequently was the number 4. And therefore, that is our mode. 4 was our mode because it's the number that we found most frequently. Now, if you recall from earlier, we had our nice little normally distributed bell. So you recall from earlier, what I'll do is we're going to move back so you can do a little recap. This was our nice little bell. I'll erase here so it makes a little bit more sense. So notice that it's symmetrical, right? It looks exactly the same if we were to split it down the middle. It looks exactly the same here as it does on this side, right? It looks exactly the same. Well, that is because if we move again to our new example, notice that we have in the normal bell, there is no skew. The mean, the median, and the mode will fall directly in the middle. It becomes a perfectly symmetrical distribution. This side looks exactly like this side because all 3 of these, the mean, the median, and the mode, remain the same. Right? Remember that generally we may find data that perhaps does not look like this, right? We're talking about IQ. IQ does look like that because we had an IQ of 100. And then we started moving towards this direction or that direction, and it was spread normally. However, we may have instances in which our data could be positively skewed. So let's look at this example. So here we have that our mode, our mean, our median, and our mean have different values, right? So we have our mode here. I'll mark this red too. And then we have our median here, our median here. And then we have our mean. We have our mean here. All right. So if you notice, in the case of a normal distribution, everything was down the middle. Everything was down the middle. There was no real difference between the numbers. So everything fell down the middle. Whereas here, notice how the mode, in this case, we have the mean was greater than the median, and what's greater than the mode. And then we look at the negative direction, so negatively skewed, you see that the mode is greater than the median, is greater than the mean. So notice that this is not normally distributed, because in a normal distribution, everything will fall in the middle. Whereas here, you're noticing that the data is pretty spread out. And in this case, it's spread out towards the negative. And in this case, it's spread out towards the positive. Now, generally, when we're trying to find a better representation when it comes to a negative or a positive, positively skewed or negatively skewed distribution, the median tends to be a better representation than the mean, because we're trying to avoid those outliers, those numbers that fall way above or way under our distribution of data. Now let's look at measures of variability, right? So if you remember from our measures of variability, we talked of our measures of central tendency, and now we're going to talk about our measures of variability. In regards to our measures of variability, as we noted before, we have our standard deviation. So how far do we move from that center, right? Now, we also have the standard error, right? Standard error. Now, there's always going to be an amount of error or variability within your data set, right? Within and between your data set. So you're always going to find an amount of error, and that's simply telling us the amount of difference, if you will, of variability that there is within that data set. Now, if we're looking at the standard error, we're actually going to have a really good illustration of standard error through error bars, and we're going to be covering standard error much more in detail. So let's look about the measures of variability that we have illustrated in our little chart here, in a little bell curve. So let's look at this red line here. That red line illustrates that there is a large amount of that data that fell in the average. So in keeping with our IQ assessment, right? There's this line in the middle. Let's try that one more time. And normally, like the bell that I showed you earlier, we would expect it to be a little bit more bell-shaped. But in this case, it looks really sharp, right? It looks like it has a peak. That tells me that a lot of the data fell very close, it's encapsulated, if you will, very concentrated towards the mean. That tells me that there's a large amount of an average. Now, a narrow distribution such as this one, such as the red one, it's better than the broad distribution. So for example, this green one here, it's going to be better for distinguishing groups. So notice that everything here fell within the mean, so there's not a lot of difference between them. Whereas here in this green line, there is a lot of difference between them. It's actually pretty broadly distributed. Remember that a measure of variability, it's simply the spread of that distribution. How far along, how is this data spread amongst this curve? Now, what are error bars? Because I know that I mentioned that earlier. Now, error bars will represent that standard error, right? And something to note is that whenever we find these error bars, if there is an overlap between these bars, it generally implies that the groups are not likely different. Now, if there's no overlap, we can conclude that the groups are likely different. Now, keep in mind that these differences are going to depend immensely on the sample size, right? We would assume that the greater the sample size, we're going to gather a more representative sample of this population. So generally that will reduce the error, right? Because we are gathering a more representative sample, if you will. Now, generally, when we are trying to represent error bars, we usually do it via the way of bar charts, and we also do it via the way of line charts. Generally, that's how we can observe, right? Because we will have that numeric value, but usually it's more easy to view this data in an illustrative sense instead of just the statistical sense. And we're actually going to see examples of that very shortly. Now, in keeping with that promise, we have, in this case, this is an illustration of error bars that I collected from this study here. And this study was trying to study whether or not skipping breakfast had some sort of impact towards stress and depressive mood. They also studied other variables, but for this example, we're only going to use stress and depressive mood. So I want you to notice that in this error bar, technically the standard error is going to have this little T-shape right here. This little T-shape right here. If you see it, I'm going to mark them down here for you. They're a little bit easier to read, right? And here we have the same thing. I'm just going to mark them so that they are a little bit easier to view. So notice that the T is going to extend below and above. I want you to note that the very top of this T shape, it's generally that extension of the mean and the error, right? So we're thinking about the base of this chart with the mean, right? So we're thinking about the base and how far up are we moving in regards of error or variability, if you will. Now here we have another illustration. Like I said, we can use them with bars and we can use it with line charts. So notice in the same example, and here we have an example of a response time and the mean response. So say, for example, if you're conducting an assessment and you're trying to ascertain the time it took for participants to be exposed or react to a particular stimuli, this is probably a good example of how perhaps that could look like. So we have, again, the score for the mean and that error in that little T-shape. Now, for those of you who are curious, this study found out that skipping breakfast increased the risk of stress and depressive mood in adolescents. If I'm not mistaken, the sample for this population was Korean Americans. So when we're talking about the representation of the sample in regards to the population, I did want to mention that, to my understanding, it had to deal with Korean American participants, although I could be wrong. But if you are interested in reading the whole study, which is always advisable, you can refer to this website here. Now, when we are talking about hypothesis testing, if you remember from earlier when we first started our lecture, a null hypothesis is that when we are not having any sort of treatment as imparted to that group, right? So we're not having that impact towards that group. We are assuming that there will be no change. And generally, that's what the null hypothesis is. We're expecting that there will be no change between these people who are receiving the treatment or not. Now, something to remember is that, in a really easy way to remember this, is that the treatment will equal the control, meaning that there is no impact, right? So generally, that's what we think about when we're thinking about that null hypothesis or that control group. On the other hand, we have the research hypothesis, or the alternate hypothesis. As I mentioned earlier, that prediction is that there will be indeed an impact with the persons who receive that treatment, right? So for example, in keeping with our example of that fictitious medication and anxiety, we would expect that there is indeed an impact between this medication towards the dependent variable, which in this case would be the amount of anxiety symptoms, or the type of anxiety symptoms, if you will, that that group is experiencing. Now, in regards to the inferential statistics, as you remember earlier, I want you to remember that the whole point of the inferential statistics is whether to infer that this change or that this treatment, this difference did in fact occur because of that treatment and not necessarily because of chance. Because of that, inferential statistics allow us to either keep the null hypothesis, which would be what I like to call the baseline, keeping that null hypothesis, which is there's simply not going to be any change, or the inferential statistics can help us say, okay, well, there will be, in fact, a change, and this is why, because we can actually ascertain the probability as to whether or not that change occurred by simply chance, or did it occur because of our treatment. Because of that, inferential statistics can actually help us accept or reject that null hypothesis and accept or reject that research or alternate hypothesis. Now, something really interesting, and we have covered the fact that we can infer the likelihood of results due to chance because of inferential statistics. We can also understand the logic between and calculate that ratio in the difference between groups or within groups. What do I mean by that? Let's go back to our little chart over here. So we have these groups, right? We have the group here who didn't skip any breakfast, right? So we have the group that skipped breakfast, the group that only skipped one time, and the group that skipped twice. So notice that we have differences between the groups. So we have a difference clearly between this group and this group and this group. So we have differences between the three, right? The three groups. But also, look how we have differences within the group, right? Because we have this difference here, right? We have the difference within the group that skipped twice. We have differences within the group that only skipped one time. And we have differences at all. We have no differences in this group, right? So we would say there's a difference between this group. There's a difference between within this group, I should say, and within this group. And in here we have differences between the groups. And same thing goes for the individuals who did not skip once or skip twice, but there's also differences, I should say, within them. There's differences within that group. Now, between or within differences, we like to think about how treatment and individual differences had a role of these differences, regarding these differences, we always want to aim for that top number, right? And that top number, generally the numerator, we're thinking about the between differences between the groups. And with that bottom number, right, we're thinking about the denominator, we're looking for it to be small within the group, right? So for example, 10 to 1, right, will be better than a 1 to 10 difference, right? Because we want to aim for that between difference rather than that within difference, right? We want to look into that between difference of no skip, skip once, and skip twice versus within the sample, right? Because we want to make sure that we find that difference in regards to our independent variable, which was in this case skipping breakfast and its relationship between stress and depressive mood with adolescents. Now, something important is that we will have to make statistical decisions, right? And these statistical decisions, the first one that we need to make is, let's find out what that data scale is. Are we using a nominal scale, an ordinal scale, interval, or ratio? What's the distribution? Does it look like my normal bell, right? Or does it look skewed, right? Does it look like a skewed bell shape? We're also wanting to know how many factors of that IV and how many levels of that IV do I have, right? So for instance, when we were talking about these levels, notice that we have that variable, but this variable had 3 levels. So we have one IV, in this case, one IV that has 1, 2, 3 levels. So we have one IV per 3 levels. Notice that's another decision that we have to make, is how many variables and how many conditions or levels do we have for each one. Now, the other thing is we need to find out what types, what sets of participants are we going to have for each condition or each level. So notice that in this case, we're going to have difference here, right? So between subjects. And what I mean by that is that different participants will get different levels of that treatment, of that IV. So for example, we have participant 1, participant 2, participant 3, and if you see, that person had different levels of, or these different people had different levels, right? So participant 1, 2, and 3. Whereas here in the within subjects, the same participant, so participant 1 was involved in all those levels. So participant 1 was involved in the second level. Participant 1 was again involved in that third level. So notice that here, different people, different participant, different levels, same participant, and all levels involved in the study. Now remember that sometimes we can always conduct parametric statistics because, like I mentioned, if we violate all of the assumptions that we noted earlier, right? So we noted in here, we noted that it has to have a normal distribution, it has to be interval or ratio data, or we have to have a sufficient sample size. So if we violate any of those assumptions, we're going to move towards the parametric statistics, I should say. Now, here in the nominal data, the only thing we will be observing would be simply the frequency, right? The frequency, the tally of data. We're basically simply counting the number in each category. So here we have 16, 40, and 44%. Now, this study that I am showing you here, this illustration is based on this study here. And this study attempted to identify or look into the stigma that subjects may have towards a patient with depression or psychosis, right? So for example, the sample here were healthcare students, right? So nursing students and things of that nature. And they were asked about their own stigma when they were dealing with individuals, or their awareness when it came to individuals with depression and psychosis. And notice that about 44% of them said that perhaps there was no stigma when it came to working with a patient that has psychosis, versus 40% yes and 16% no. So notice that here in this information, we're simply tallying. We're simply conducting and counting numbers of a category. So there's 3 categories here: yes, no, don't know. So we're only telling the frequency of these 3 categories, right? These 3 bins, if you will: the yes bin, the no bin, and the I don't know bin. Now, if you're interested in the results of that study, the results showed that the stigma of subjects towards patients with depression and psychosis was present, and it was higher for psychosis. So there was indeed a higher form of discrimination towards patients who were experiencing psychosis. I do want you to remember these people did indeed have awareness when it came to mental illness. So these individuals were laypersons, if you will. They were aware of differences in psychosis, but I thought it was a really neat example to include here. Now, with our parametric statistics, as I noted, we have to utilize interval or ratio data. Now, another interesting factor about this is that we need to compare 2 groups. So in this case, we're going to have an experimental group and a control group. Now, there's multiple ways that we can ascertain these comparisons. So the first one, we can conduct an independent t-test, which means that different subjects are in each level, right? So in keeping with this, we have different subjects at different levels. So level 1, 2, 3, participant 1, 2, and 3. Now, in the dependent t-test, we have the same subjects in each level, right? So we will keep those same people in the same level. Now, we can also conduct a multi-group comparison, which is when we have one IB, right? One independent variable, and this independent variable has 3+ levels, right? So we have an independent variable, and we have the medication, people who received the medication, people who did not receive the medication, people who received the placebo, and say people who received another medication for anxiety. So that would be an interesting way to conduct a one-way ANOVA. Now we can also conduct a multifactorial. So we're thinking about more than 2 independent variables when we are conducting a multifactorial study, because again, we're trying to find that comparison. I'm trying to compare whether or not there was differences in these groups. So we can conduct a 2-way ANOVA, or it could be based on the number of factors, right? And the number of independent factors. So here's an illustration of this previous slide. So we have one control and treatment number 1. So this perhaps falls within the t-test, right? So this falls within the t-test assessment. Now, in this case, we have the control, right? We have treatment 1 and treatment 2. Perhaps this falls within the realm of ANOVA. Keep in mind that for this design, we're only looking at one factor, right? So for example, just that one IV, okay? We're only looking at one factor only. Now here, we're looking at multiple factors. So for example, we have A, and A has 1, 2, and 3. And B has 1 and 2. So notice that in turn, that leaves us with 6 different levels, right? 1, 2, 3, 4, 5, and 6. So this leaves us to this design that has six factors, or I should say 6 groups in it. Now, why do we care about significance, right? As I mentioned earlier, we may have a difference, sure. We can't find the participants who had that medication did in fact have, they did actually have less symptoms of anxiety. But was this difference meaningful? Was this actually statistically significant? Well, significance means that I can indeed reject that null hypothesis, because for all we know, yes, there was a difference, but it wasn't enough to actually accept that, yes, it indeed was different. There is actually a difference and an impact towards this variable, towards the dependent variable. Here, we have to infer that that difference was in fact because of that manipulation and not by chance. And generally, when we look at the letter P, we're actually looking at probability. This is how we consider that there was an impact on this variable. So when we have that this probability was less than 0.05, what that is telling me is that this is a method of us understanding probability, that indeed it was a less than 95% chance that this occurred by chance, that this occurred because of nothing other than chance. But vice versa, if my probability is greater than 0.05, we may actually have to accept that null hypothesis, because there's another possible explanation that chance could have contributed to that difference. Now, in looking into the effect size simply describes how meaningful that significance was. So here in the p-value will matter. The sample size will indeed matter when it comes to the p-value. The effect size is generally a better estimate of the true impact of that manipulation. Now, there's multiple aspects, there's multiple ways that we can conclude and conduct the effect size within our data. So we have cohorts D, and generally we use this for a t-test, eta squared, which usually we utilize in ANOVA, and an R squared when we're looking into a correlation. Now, that last slide represents aspects that you will cover much more in detail when you are taking statistics, particularly when you start conducting your intro statistics. But this presentation basically covers an overall sense of quantitative statistics. What are they and what do they look like? And generally, once you start conducting statistical analyses in your statistics class or in your research class, that's when you are actually doing this, rolling up your sleeves, hands-on, and actually conducting these statistics yourself. I hope that this lecture was beneficial for you and that it shed some light in what types of quantitative statistics we have available for us in the social sciences. And thank you for your attention.